Hello and welcome to Note Quiz number 2, which is all about radical and rational expressions. The goal of the first several of these problems is to simplify down radicals, and the most important rule to keep in mind is that the power on the variables inside of the radicals must always be smaller than the index out front. So for this first problem, we're going to take the square root of x squared. And typically you would think that, okay, well that's just x. Problem is, if you substitute a negative number in place of x and just canceled it out, you would get a negative answer. And square roots give you only positive answers, so to get that requirement in place, we put absolute values on the x. For the second problem, we take the cube root of y cubed. You might be thinking that, okay, I'm going to get y, and now I need absolute values. The truth is we don't need absolute values because the cube root of a negative number can be negative. So it's just simply y. As a shortcut or a simple thing to remember, even roots of even powers require absolute values when the answer could possibly be negative, but odd roots do never, ever, ever require absolute values. Okay, for these next two problems, we're going to be simplifying down a cube root and a square root. For a cube root problem, you have to ask yourself, what are you being raised, or what is being raised to the third power to create this? And first of all, if we look at c to the ninth, we know that if we were to cube the third power on c, we would end up multiplying the powers together to get c to the ninth. So we know that c cubed is the first part of the simplification. To get a d to the sixth, same idea. What raised to the third power would make d to the sixth? And it's got to be a d squared because, again, when you raise a power to a power, you multiply the powers. So that's c cubed d squared. Please note that we wouldn't need absolute values if these were allowed to be positive or negative variables. But from this point forward in the guided notes, we're going to assume that everything is positive to help simplify down the thinking process. All right, now let's move on to the next problem. The next problem is us taking a look at the square root of p to the 7th, q to the 12th. Easiest way to think about this problem is to find the biggest perfect square that goes into p to the 7th. That's a p to the 6th times p to the 1st. And q to the 12th is already a perfect square. What times itself makes p to the 6th? That's p to the 3rd. What times itself makes q to the 12th? That's q to the 6th, and there is a p left over inside the square root. So p cubed, q to the 6th, times the square root of p is my answer for that problem there. And I'll kind of draw a red box around it just to kind of keep the answer separate from the calculation that we did. As a quick check, by the way, remember that a square root has an index of 2. 2 does go into 7 3 times with 1 left over, and q does go into 12 6 times with nothing left over, so you can check your powers. If you backtrack to problem number 3, 3 goes into 9 3 times with nothing left over, and 3 does go into 6 twice with nothing left over, and that's a simplification. So you can actually use division if you're very careful with these simplification problems. Okay, for this next problem, we want to simplify down the square root of 48. And the best way to simplify down square root problems is to ask yourself, what is the largest perfect square that goes into the number? And 4 does go into 48, but we can get a little bit bigger and grab a 16. 16 times 3 makes 48. So this is going to be the square root of 16 times 3. I can now break apart the square root over the 16 and the 3. And this simplifies down to 4 times the square root of 3, which is my final answer. For the next problem, we want to break apart the 72 by asking ourselves again, what's the largest perfect square? And that is a 36. So this is going to be 7 times the square root of 36 times 2. For the middle, we're going to have a 3 out front being multiplied. 63 can be broken down as 9 times 7. That's the largest perfect square is 9. And then 32, we can break that down as 16 times 2. When we now break apart the radical, we can show this extra step here, which is kind of helpful by breaking it apart over the multiplication. And then we have the 7 times the square root of 36. Well, the square root of 36 is 6. So that's 7 times 6, which is just 42, square root 2. In the next problem, the square root of 9, or I should say next problem, but the next term, square root of 9 is 3. 3 times 3 is 9, so that's 9, square root 7. And then finally, the square root of 16 is 4, so that's plus 4, square root 2. Now, remembering the rules of adding and subtracting radicals, we can only add and subtract like radicals. They have to be the same index and the same number inside. So that means that we can combine the square root of 2, but we cannot combine with the square root of 7. So 42 plus 4 square root 2 is going to be a total of 46 square root 2. So I'll write that in black. We're going to have a 46 square root 2 minus 9 square root 7. And we can't go any further with this problem because we now have two roots that are different and they cannot be simplified to be combined. All right, let's move on to the next page. And for this next page, we're going to be multiplying and simplifying down some square roots. When we multiply square roots, we want to think about the numbers in front of the square roots, think of them as coefficients. They will multiply with other numbers in front of the same radical, and the stuff or the numbers inside, the radicand, will be combined with the other ones inside. In other words, multiplying these together, you will see that we can multiply the negative 7 and the 3, and that's going to make a negative 21. And then a fifth root times another fifth root makes another fifth root. So that's going to be a fifth root of our product. And then we're going to have x cubed times x squared is x to the fifth. And then if you ask yourself, what would I raise to the fifth power to get x to the fifth? Well, that's obviously just x. So that's negative 21 times x is our final answer there. And again, no need for absolute values because everything was assumed to be positive. For the next problem, we're going to multiply these out, and we're going to use the FOIL process because we have two binomial expressions being multiplied together. So for the first, we've got a 6 times a 1 is going to give me a 6, and then multiplying the numbers inside the square root, that's going to be a 49 from 7 times 7. Moving on to the outside, 7 times 2 is 14. There's no numbers in front besides 1, so that's the square root of 14. On the inside, 9 times 6 is 54. And we once again have 2 times 7 inside the square root for a 14. And then finally, for the last terms, we have 9 times 1. And then square root of 2 times the square root of 2 is the square root of 4. Now that's going to be 6 times the square root of 49, which we know is just 7. We can now combine the middle because those are like terms. So if you've got 54 of something and you lose one of them, you now have 53 of them. So that's going to be 53 square root 14. And then the last, that's going to be minus 9 times the square root of 4, which is 2. So that's going to be 6 times 7, which is 42. Plus 53 square root 14 minus an 18. We don't have much room left, but that's going to equal 42 minus 18, which will be 24, I believe. It should be 24. And that's going to be minus 53 square root 14. And again, because we ran out of the room, I'll draw a little box around there to keep that all together for us. Okay, for this next problem, we're going to also use FOIL to multiply it out. So we're going to first multiply square root of x times square root of x that makes square root of x squared. Multiplying the outside, that's going to be 6 times the square root of x. Multiplying the inside, that's 4 times the square root of x. Then the last term, 6 times 4, is 24. We can simplify the square root of x squared as simply x because it's positive. 6 square root x plus 4 square root x makes a total of 10 square root x. And 24 is just 24. We cannot combine those terms, so that is our final answer. Which again, we'll just box it up so that we can kind of keep our answers nice and separate. For the next problem, be very careful. We are not allowed to throw around squares. Instead, we have to use the definition of squaring. Squaring always means something times itself. So that is the square root of p minus the square root of 5 twice. Just like the previous problem, we now FOIL it out. Square root of p squared minus square root of 5p minus another square root of 5p, and then finally plus the square root of 25. Well, we can now combine like terms. We have 2 of the same thing in the middle. We know that the square root of p squared will just be p. The middle, we have 2 of them, so that's minus 2 square root 5p. And then finally, the square root of 25 is just the number 5. So that is our multiplied out and simplified answer for that one. Okay, for our next group of problems, our goal is to rationalize the denominator. And rationalizing means that we want to rewrite the given expression without a radical in the denominator. So to do that, it's actually very simple for the first problem. We want to turn the square root of 2 into a nice, clean whole number or integer number. So we're going to multiply by the square root of 2 over the square root of 2. At first, it looks like we're making matters worse, but in simplifying this, 1 times the square root of 2 is the square root of 2, and the square root of 2 times the square root of 2 is the square root of 4, so that turns into just the square root of 2 divided by the number 2. And that is considered rationalized because the square root is no longer sitting on our number in the denominator, and we also have a nice calculation we can do. So this is the square root of 2 divided by 2 is our final answer. Be careful not to cancel out those 2's. You can never cancel numbers inside of radicals with those outside of radicals. For the next one, we're going to rationalize the denominator again. This time we multiply by the square root of 3x over top of the square root of 3x. Again, we're just multiplying by 1 and not changing value. In our numerator, we get 6 times the square root of 3x. Down below, we're going to get the square root of 9x squared, which is just 3x. We can do a little bit of simplifying here because the fact that we have a 6 and a 3 that are outside of a radical, and we can divide the 3 into the 6 to get 2. So final answer is going to be 2 square root 3x over top of x. For this third example, it's a little different because we have a 4th root down below. And so to simplify it down, we have to build a 4th power. We already have 1x already down there, so we're going to multiply by 3 more x's. So it's going to be the 4th root of x cubed above and below in our fraction. Multiplying straight across, that's just negative 7 times the 4th root of x cubed. Down below, that is the 4th root of x to the 4th, which we all know is going to turn into just plain x. So final answer is negative 7 times the 4th root of x cubed all over x. And again, we'll box these up just because we have a lot of calculations in a small amount of space. For the next 2 problems, the tactic that we used for the first 3 is not going to work because we have a sum or a difference in them, in particular the differences. So for these problems, we actually multiply by the conjugate, which is the same exact expression, but with the sign reversed in the middle. So we're going to multiply by 7 plus the square root of 3 above and below. Now we distribute the 2, so 2 times 7 is 14 plus 2 times the square root of 3 for our numerator. Down below, we will FOIL this time around and show you how things simplify down. 7 times 7 is a 49. We're going to get plus 7 square root 3 minus 7 square root 3 minus the square root of 9. And you will notice that those two middle terms are going to cancel out, and they do that every time we multiply by the conjugate. And you will also further notice that the square root of 9 is really just a 3. So this is going to be 14. I'll put it over here actually. 14 plus 2 square root 3. And for our denominator, that's going to be 49, take away 3, which is going to be a 46. We can actually go a little further because we have even numbers as coefficients. If we divide everything through by 2, 14 divided by 2 is 7. 2 divided by 2 is 1. We're not going to write it. And then down below, 46 divided by 2 is 23. So that actually simplifies down to this expression here. For the next one, we're going to once again multiply by the conjugate. It's going to be the square root of y plus the square root of x above and below. Upstairs, we just distribute the 9 square root y plus 9 square root x. Down below is where all the magic happens. We get the square root of y squared plus the square root of xy minus the square root of xy minus the square root of x squared, which we know simplifies down further. Once again, middle terms cancel out when you multiply by the conjugate. Upstairs, we've got 9 square root y plus 9 square root x. Down below, y minus x, because those square roots cancel out. And that's as far as we can go for that problem there, because we have nothing that can cancel. All right, so let's move along to the next page. For the next page, we're going to work a little bit with some complex numbers for these next couple of problems. So for the first problem, what you want to do is you want to take the square root of negative 144. And we know there's not a real number that does this because you can't multiply something times itself and get a negative answer when they're real numbers. So what we're going to do instead is we're going to go through and rewrite that negative 144 as 144 times a negative 1. And then we're going to break apart the square root as the square root of 144 times the square root of negative 1. Now, see the upper edge of the multiplication table, but that is actually 12, because 12 times 12 is 144. And now this is the part that's kind of interesting mathematically. We're going to have the square root of negative 1. And that's really what we have here. But mathematicians hundreds of years ago decided to replace that number with the symbol I. And that's called the imaginary unit. And we're just doing that to rewrite this in a much shorter notation than that cumbersome square root. So 12i is the answer that we simplified down to. And remember again, that is not a real number. It's called an imaginary number because of the fact that it's not real. Next up, we're going to multiply and simplify down. Once again, this is a FOIL problem. So multiplying the first, 7 times 7, we know is 49. We actually saw that earlier in this lesson. 7 times 10 is 70, so that's a minus 70i. The middle is 10i times 7, that's plus 70i. And then finally, minus 100i squared. You should notice here these two numbers are actually conjugates because it's the same exact expression, but with the sign reversed, just like we saw on the previous page. No surprise, the middle terms cancel out. So this is actually a 49 minus 100i squared. Well, I squared is actually going to be equal to negative 1 because I, by definition, is the square root of negative 1, and I squared is us squaring the square root. So that's just going to be a negative 1. So that's actually minus 100 times negative 1, which is going to be actually 49 plus 100, which simplifies to 149. And you will notice that if you take a complex number and multiply it by its conjugate, you always get a real number. It's a nice little property we have. Next up, we're going to simplify down some complex numbers just to get some more practice. We're going to be seeing these a lot later on in the semester. So for starters, we're going to factor out an 8 from the numerator. We get 1 plus 2i. You can rewrite the 24 as 8 times 3. Cancel out the common 8s. You get down to a 1 plus 2i over 3. But we can't leave our answer this way because we want to express our answer as a true complex number, which has a real part plus an imaginary part. So we're going to split this number up as 1 over 3, or just 1/3, plus 2 over 3 times I. And now we have ourselves an honest-to-goodness complex number. For the second part, this is really foreshadowing quadratic formula because this is what we're going to see coming up. So this is going to be a negative 9. And then we're going to take apart our 72 with a 36, a 2, and a negative 1. All over top of negative 6. That square root of 36 is actually the number 6. The square root of 2 is stuck as the square root of 2. The square root of negative 1 is really an I. That's all over negative 6. We can now split this apart like before. This is negative 9 over negative 6 plus 6 square root 2 times I over negative 6. 9 over 6 reduces down to 3/2. And then we have a minus. The 6's cancel in front of that radical and below it. So we're going to have the square root of 2 with an I. And just be very careful. You do not want to put that I under the square root. It could be in front or behind, but never underneath. All right, so we're now going to switch our gears and start talking about rational expressions. And the most important aspect of them is remembering that you're never, ever permitted to divide by 0. A 0 in the numerator is okay, but never allowed in a denominator. So what we're going to do is we're going to take our denominators and make sure that they are never 0. So we're going to take w squared minus 2w minus 8, and we're going to set it not equal to 0. And then we can factor this as w minus 4 and w plus 2 is not 0. And then we can set each of these factors not equal to 0. So w cannot be 4, and w cannot equal negative 2. We're going to put the answer in set builder notation, which means we're going to dress them up with set brackets. It's going to be the set of w's, where w is not 4, and w is not negative 2. And close up your set bracket. I'm going to do the same thing for the next problem, except the factoring this time will be a little bit more challenging. This time around, we've got 2x squared minus 5x minus 3, not 0. So this time around, we'll do the AC method. We'll take the 2 times the negative 3 and get negative 6. And find a pair of numbers that multiply to make negative 6, but add up to make negative 5. They are negative 6 and positive 1. So this is 2x squared minus 6x plus 1x minus 3 is not equal to 0. Because we have 4 terms now, we're going to group the first 2 and the second 2. In the first, we can take out a 2x, leaves us with x minus 3. In the second, we can take out a 1, leaves us with x minus 3. And then we can take out the common x minus 3, and we're left with a 2x plus 1. And again, those two factors, we want non-zero. That means that x minus 3 must be non-zero, or 2x plus 1 is non-zero. That means x can't be 3, and 2x can't equal -1, or x can't be equal to -1/2. So this is going to be the set of numbers x, such that x is not equal to 3, and x is not equal to -1/2. Write that really nice and small. So that is going to be the set of possible answers there. And this is going to be the set of possible answers for the first one. So we found the restrictions for the first expression and the second expression here. All right, so let's move on to the next page now. And you'll notice that the first thing they're going to ask us to do is to simplify down the rational expressions. And this is where you have to be very careful, because a lot of people have the tendency to want to cancel through pluses and minuses, and we can't do that. We'll get the wrong answers. So even though those t squared over t squareds are very tempting, please don't cancel them. Instead, we cancel common factors, which means we have to factor. Upstairs in our numerator, we can find two numbers that multiply to make -10 and have a difference of 3. It's going to be t plus 5 and t minus 2. Down below, we're going to factor that. Two numbers that multiply to make a positive 8 add up to make a -6. That's going to be t minus 4 and t minus 2. And again, don't forget, you can always check your work by multiplying by FOIL and comparing to the original. You will now notice that I can cancel out the common t minus 2's. It's a package deal canceling out. And I'm left with a t plus 5 divided by t minus 4. And we can't go any further with this, even though, again, those t's are tempting. Do not cancel them. You'll get the wrong answer. So that's t plus 5 over t minus 4. Once again, we'll box it up just to kind of keep it together. All right, for the next problem, you will notice that those two factors, the one above and one below, are very similar looking, but they are different. The subtraction's been reversed. Easiest way to handle these is to factor out a -1 from either the top or bottom. Let's do it for the top. So that's -1 times -15 plus x, and then down below you still have x minus 15. You will now notice that I can rewrite the stuff upstairs as x minus 15. Down below is still x minus 15. Those are now a perfect match. They're exactly the same, so I can cancel them out. But this time around, when I divide something into itself and it's an opposite, I get a -1 left behind. Over here, when I divided something by itself, I got a 1 left behind. So this simplifies down to just -1. And that's going to be recognizable by the fact that the original, they were opposites of each other, reversed subtraction. All right, so now let's move on to multiplication and division. For this first problem here, you will notice that we're going to multiply together two rational expressions. So we have to follow the rules of multiplying fractions. The rule is we multiply straight across. So this really looks like we're going to be gluing together, and that's what I like to call it. This is a 6q minus 4 multiplied with 2q squared minus 3q minus 14 over top of q plus 2 times 9q squared minus 4. Believe it or not, the last thing you want to do here is actually multiply this stuff together, because you'll get a really complicated expression over top of another one. Instead, we're going to factor and cancel. For the 6q minus 4, I can take out a 2. Leaves me with a 3q minus 2. For the other part, we're going to factor as well. I wrote that a little big. Let me downsize that. And then down below, we've got a q plus 2. And then we can factor the 9q squared as a 3q. And the 4 is a difference of squares, so that's going to be plus 2 and a 3q minus 2. So the next thing to do is now factor the top. And again, you could either use grouping or you could just use reverse FOIL with a little bit of carefulness. So the only way to get a 2q squared is going to be a 2q and a q. Now we got a split apart of 14. And you should be thinking 2s and 7s. So the idea is you might want to take a peek at what else is going on in this problem. So we probably are going to have a q plus 2 and a 2q minus 7 to have this cancel down further. I don't know that for sure. I should probably multiply this out and check to be safe. 2q times q does make 2q squared. 2q times 2 makes 4q. And from the middle, we got minus 7q. 4 minus 7 does make minus 3. And then finally, minus 7 times 2 does make negative 14. So that is the correct way to factor it. And again, you could just use the AC method off to the side and then put the answer in the space. Next up, time for a cancel fest. You will notice I can cancel out the q plus 2's, and I can cancel the 3q minus 2's as well. And I'm left with a 2, a 2q minus 7 over 3q plus 2, which is my final answer for that one. So I'll put that down in the space so I don't forget. All right, now let's move on to the other problem. I'll put up a little divider just to kind of keep everything separate. So this is a division problem. And division always has us multiplying by the reciprocal of whatever we're dividing by. So this is the same exact thing as x squared minus 16x plus 64 over the x cubed minus 3x minus 40. Now times 2 over x squared minus 64. Again, we multiplied by the reciprocal of what we're dividing by. Next step is to do this just like the previous problem. We're going to factor and glue it together. You'll notice that I can factor the first one very easily because two numbers that multiply to make 64 and add up to 16 are just 8 and 8. So that's x minus 8 twice. I still have that times 2 trailing behind it. Down below, that was actually an x squared. My apologies. Let me fix that. Use reverse FOIL. Two numbers that multiply to make 40 and have a difference of 3. Well, I'm going to say that's x minus 8 and x plus 5. And then back there, the x squared minus 64 is the difference of squares. So that's x plus 8 and x minus 8. Now we're set up again for a nice little cancel fest. X minus 8's canceled out of there. X minus, like that's cancel, but I didn't want to erase it. That was really an x minus 8 before I destroyed it. And that x minus 8 cancels with that one. And I'm left with a 2 sitting over top of x plus 5 times x plus 8. And once again, we will box them up so we can have our answers accounted for. All right, so let's move on to the next page. And the next page is going to have us doing a combination of different operations. The first problem is a division that we just looked at earlier. That's going to have us dividing. So first up, we're going to go in and rewrite this as a multiplication problem. That's 5y minus y squared over y cubed minus 125 times the reciprocal, which is now y squared, plus 5y plus 25 over top of y. So again, every division turns into a multiplication of the reciprocal. Now let's factor very carefully. That first, I can take out a y, leaves me with 5 minus y. We cannot factor that trinomial because you cannot find two numbers that multiply to make 25 and add up to 5. Down below, y cubed minus 125. Yeah, we saw that just recently. That's the difference of cubes. That factors as y minus 5 times y squared plus 5y plus 25. And don't forget you have that lonely y sitting down there from before. And would you look at that? Those two trinomials are perfect matches. They cancel right on out. So they are gone. We can also cancel out that 5 minus y and that y minus 5. If we remember again that they're opposites and leave behind a negative 1 behind them. So that's actually almost canceled out, but I almost missed something, didn't I? If you look further, you'll notice I've got a y over a y. That can cancel out as well. What I'm left with is really just a negative 1. I guess this is a bit of irony you have sometimes. So there we go. That simplifies down to just a negative 1. We're now going to move on to subtraction. And subtraction is very different from multiplication and division. We have to have a common denominator to add or subtract fractions. And to build those, we often have to factor down our denominators and build an LCD. So for the first one, you will notice that I can take out a common 6 and I'm left with b minus 7. And then back there, I've got a b plus 2 over a b minus 7. Those denominators are similar, but they're not the same. They need to be exactly the same to add or subtract. So what's missing here is a 6. I need to put a 6 down there where the b minus 7 is. So I multiply by 6 down below, and I multiply by 6 up above because I'm only allowed to multiply by the same thing in the top and bottom because I'm multiplying by 1 and not changing value. All right, so next up, my new denominator is going to be 6 times b minus 7. Upstairs, I've got the original 7b plus 5 on the left side. And now I have to carefully distribute that 6 to both the b and the 2. So that's going to be minus 6b and then minus 12. They're both minus because that negative belongs to both of those terms. Combining 7b minus 6b is just one single b. And then 5 minus 12 is negative 7. That's over 6 times b minus 7. And once you know it, we've got a common factor we can cancel out. And remember, when something divides into itself, it goes in one time. So final answer is 1/6 from all of that calculation. Okay, for our next problem, you'll notice it's a subtraction, and therefore we need common denominators. Well, that first one, it's not exactly the same, is it? So let's just kind of copy this problem down so we have more room to work with it. So that's a minus 5 minus a plus 5 over 7 minus a. So a minus 7 and 7 minus a are opposites. The easiest way to handle this problem is to multiply the top and bottom by a negative 1. You can actually pick either of the two denominators, but it's better to pick this one. All right. Now we're going to have a minus 5 over a minus 7 still. But back there, you will now be able to bring together that negative and that negative, and they're going to turn into a plus. A plus 5. Down below, that negative 1 times that negative a makes a positive a. That positive 7 times that negative 1 makes a minus 7. You now have the same denominator, so you can add these up. Your denominator is going to be a minus 7 upstairs. A plus a makes 2a. And then you have the minus 5 plus 5. That's just a 0. So you're going to get a 2a over a minus 7 for your final answer here. All right, the next problem is going to be a big one because we need to add together these two fractions that have a lot going on in their denominator. So what we're going to do is first factor. We've got a w minus 4 down below. W squared minus 9 is a difference of squares. That's w plus 3. And w minus 3. Back here, once again, I'll factor my denominator. Two numbers that multiply to make 18 Adding up to 9 is 6 and 3. So it's w plus 3 and w plus 6. We now need to find the LCD, and I'm going to write that off to the side in red just so we have it for reference. The LCD is going to be the smallest combination where all of the denominators divide into it evenly. The first fraction requires us to have w plus 3 and w minus 3. For the second fraction, it's already got a w plus 3, so it just needs the additional w plus 6. And now that is the smallest combination of factors where both the first fraction goes into it down below, and so does the second fraction. Next up, we multiply the top and bottom of each fraction by what's missing. So the first one is w minus 4 over top of w plus 3, w minus 3. What's missing is the w plus 6. So we do that above and below. And again, we're just multiplying by 1. Back there, we've got the w plus 3 and the w plus 6 already there. What's missing, of course, is the w minus 3. Put it above and below. And again, we are just multiplying by 1. Upstairs, I now use FOIL. I've got w squared plus 6w minus 4w minus 24. Back there, I'm going to have a minus w squared plus, again, be very careful here. With that negative and that negative, that makes plus 3w. And that's over my brand new denominator, which is w plus 3, w minus 3, and w plus 6. And again, the order down there does not matter. Now let's simplify. You will notice I can cancel out my w squares because they're opposites. If I count up my w's, I've got a total of 6 minus 4 is 2 plus 3 makes 5. I've got a 5w, and there's nothing for the 24 to combine with, so it's alone. So my final answer is 5w minus 24 over the trio of w plus 3, w minus 3, and w plus 6. And even though it looks kind of strange and kind of ugly, what we've done here is we took two fractions, subtracted them, and got a fraction for an answer, and simplified it down as far as we could. All right, so let's move on to the next page, and the next page is going to begin some computations with complex fractions. There's a lot of different ways to handle complex fractions. I'm going to show you what I think is the easiest way to handle them. And what that is going to be involving is eliminating denominators. So let's kind of show you how that works. Remember again that you can always multiply by 1 and never change the answer. So I'm going to multiply by something to get rid of my denominators. And that something is going to be 8. So I multiply the top and bottom by 8 over 1. Technically, I'm really multiplying top and bottom by 8, but the over 1 helps keep it lined up. Now, upstairs, you will notice that the 8s are going to cancel out, and I'm left with just plain r plus 4. Down below, not so good, but still not too bad. The 8 and the 4 cancel out and leave behind a 2. So there's a 2 and the original 16 minus r squared. And you must admit that's a lot nicer looking than the original complex fraction. Next step, try to simplify if we can, and you will notice that I have the difference of squares. That's 4 plus r and 4 minus r. And I can cancel out those r plus 4s and 4 plus r's because they're exactly the same. Leaves behind a 1. Final answer is 1 over 2 times 4 minus r. And that's a perfectly acceptable way to leave that final answer there. For the next problem, you will notice that I can once again find something to cancel out my fractions. This time around, I'm going to multiply by x squared over 1 in the top and the bottom of the fraction. Again, that's a strange looking 1, but it is 1. Next thing to do is distribute. So in distributing, I'm going to get a 4x squared over x plus 7x squared over x squared. Down below, 4x squared over x squared minus 9x squared over x. And now you'll notice I can cancel out a lot of stuff. 4x squared over x is just plain 4x. 7x squared over x squared is just 7. 4x squared over x squared is just 4. And 9x squared over x just simplifies down to 9x. So my answer is 4x plus 7 over 4 minus 9x. And that is my simplified answer. For our next problem, I once again want to find something I can multiply the top and bottom by to cancel out my fractions. And for this problem, it's going to be c squared. And again, we're going to put it over 1 to keep everything lined up nicely. Once again, distributing, that c squared, it's going to hit all 3 of those. And this c squared is going to hit all 3 of those. So this time around, we'll try something a little different. We will cancel as we go. So the first one is just 1 times c squared, which is just c squared. In the middle, I'm going to get c squared over c, which is just plain plus c. And then back there, 12c squared over c squared is just minus 12. Down below, I'm going to have 27c squared over c squared. That's just 27. In the middle, I have minus 3c squared over c. That's just minus 3c. And then finally, minus 2c squared. This may cancel down further. Best way to find out is to start factoring very carefully. Upstairs, you will notice that I can find 2 numbers that multiply to make negative 12 and have a difference of 1. That's 4 and 3. So that's going to be c plus 4 and c minus 3. Down below, I'm going to do myself a huge favor and factor out a negative 1. You can see with 2c squared plus 3c minus 27. And then off to the side, let's try factoring that. We've got 2c squared plus 3c minus 27. I'm going to use the grouping method this time around. 2 times 27 is 54. 9 times 6 is 54. So that's 2c squared plus 9c minus 6c minus 27. Factoring, I can take out the greatest common factor of c. I've got 2c plus 9. Back there, I can factor out a 3. And I'm going to have 2c plus 9 is 2c plus 9. I lost my c. So 2c plus 9 factors as 2c plus 9 times c minus 3. So that's going to go back over here. C plus 4, c minus 3 over top of negative 2c plus 9 and c. Yeah, I can write that a little nicer. C minus 3. There we go. And once you know it, those c minus 3's can cancel out. So a final answer, when it's all said and done, is negative c plus 4. I'll put parentheses around that over a 2c plus 9. And that negative could also be out in front of the fraction as negative c plus 4 over 2c plus 9, but people usually write parentheses around it to keep it all together as a package deal, like so. And that right there is our complex fraction simplified down. All right, so let's move on to our next page, which will have a few more of these rational expressions. Our first one, it'll be just adding together some kind of whole number quantities of fractions. Easiest thing to do is put that first term, h plus 8, over 1. And now our LCD for this problem is just h plus 8. So we're going to multiply the top and bottom by h plus 8. So we have the original h plus 8 already there, sitting over top of 1. We're going to multiply by h plus 8 in both spots. In the second one, it's 1 over h plus 8 already. So it's got that denominator we needed. Next thing to do is FOIL out the top. So that's h squared. 8h plus 8h makes 16h. Plus 8 times 8, which is 64, over top of h plus 8. Now that's added to 1 over h plus 8. So adding that together, we get h squared plus 16h plus a 65 over top of h plus 8. So h squared plus 16h plus 65 over h plus 8 is my final answer for that one. Again, we basically added together a number and a fraction and got an improper fraction, if you will. Next problem is a little bit of foreshadowing. This looks a little bit like a difference quotient, and we'll talk more about that in the coming weeks. But in the meantime, we're once again going to get common denominators. So first thing I'm going to do is make that an h over 1 and rewrite this as negative 8 over x plus h plus 8 over x, now times the reciprocal of the denominator, 1 over h. All right, next up, identify my LCD. Remember, LCDs are only built by multiplying stuff together. You can't add or subtract to build them. So the first term requires x plus h. It must be there. The second one requires an x. Next thing to do is multiply the top and bottom of each fraction by what's missing. So the first one is missing an x, so I'll multiply the top and bottom by x. The second one is missing x plus h, so I'll multiply by x plus h in both spots. All right, and that whole thing is still multiplied by 1 over h yet. All right, next up, I'm going to have my common denominator of x times x plus h. In my numerator, I've got negative 8x from the first. Distributing, I'm going to get 8 times x plus 8 times h. Still times 1 over h. Now you'll notice that I have some opposites I can cancel. That negative 8x and 8x, they're gone. So if I continue this over to the other side, I'm going to have an 8h upstairs, and then down below I've got the x plus h, and I might as well bring over that h which has been hanging out behind it. You'll notice my h's cancel out, and I'm down to a final answer of 8 over x times x plus h. And that is what that simplifies down to. And again, in the coming weeks, we will call that a difference quotient. All right, now let's move on to the final page. And the final page has us coming back to radicals. So skipping over to the next page, you will notice that we have a bunch of expressions that have fraction or rational exponents. So what's a good idea here is to review the rule from intermediate algebra of how to deal with these things. And that rule, for the record, is if you have x raised to the m over n power, your fraction exponent, that is the nth root of x to the m, or it's the nth root of x raised to the m power. Either way, the number on the denominator is your index or the power of your radical, and then the exponent is the numerator, and that goes on the base. So for this first one, the c raised to the 2/3, we know it's going to be a cubed root of c squared. And that's all it is. Cube root c squared. For the next one, we're going to go backwards. So because we have 5 as the index, it's a fifth root. That's our denominator. Because 4 is on the a, that's our numerator. That's a to the 4/5 power. All right, next up, we're going to keep the same idea going, but this time around you see a negative exponent. Remember, those are reciprocals. So the idea here is that you want to rewrite this as 1 over 36 to the half power. Well, the half power is a strange one because the 2 is the square root, and we don't write it. And the 1 is the first power, and we don't write that either. So this is actually 1 over the square root of 36, which is just a 1/6. Next up, we've got 4 raised to the negative 3/2 power. First thing to do is get rid of that negative power by taking the reciprocal. Be careful, don't flip your fraction. You just put the whole thing under 1. This now becomes 1 over the square root of 4 cubed. It's easier to take the square root first. Square root of 4 is 2, so that's 1 over 2 cubed, which is just 1 over 8. So 1/8 is your answer. Next up, I'm going to go through and rewrite these first as radicals. Because the 3 is down below in your fraction, that's a cube root of 64 c to the 6th. I can either square the 64 and the c to the 6th, or I can square the whole answer. A lot easier to square the final answer. Cube root of 64, that's 4. Cube root of c to the 6th is c squared. That whole thing is still squared yet. 4 squared is 16, and c squared squared is c to the 4th from multiplying the 2's. So 16. 16 c to the 4th. Here, because the 2 is our denominator, that's the square root of 64 c to the 6th, whole thing cubed. Square root of 64 is 8. Square root of c to the 6th is c cubed. Whole thing is to the 3rd power. If we take 8 and we cube it, that's really 8 times 8 times 8. That's 512. C cubed is just c to the 3 times 3, so that's c to the 9th. So 512 c to the 9th. You notice that having the 2/3 power and the 3/2 power give you totally different answers, and that's not a surprise. We should expect that kind of stuff. All right, so that right there is the final page of note quiz number 2. Again, make sure you do your work in ALEKS to get your credit for your Pi progress, and make sure that when you're finished up with your notes, scan them and upload them in Canvas.